Okay, so as a reminder of what we did last class, we ended class by learning the test for concavity, or the concavity test, which told us that if the second derivative is positive, then the function is concave up, which means it's happy. And if the second derivative is negative, that means it's concave down, which means it's sad. And then we learned that the places where a function changes concavity are called inflection points if f is continuous at those values. We also learned that inflection points occur when the second derivative equals to 0 or the second derivative does not exist. So these are kind of the main things that we're going to be moving on from today. Inflection points, that's when we change from happy to sad or sad to happy. That's called concavity. And the second derivative gives us information about that. So today we're just going to start off assuming that we remember that stuff, and we're going to have some guidelines for applying the concavity test. Guidelines for applying the concavity test. And these guidelines are going to be really similar to the guidelines that we had for the test for increasing and decreasing. We're going to do everything exactly the same, except that we're using the second derivative instead of the first derivative, which means that our first step here is to find f double prime. And once we found f double prime, we want to simplify it. The next step is to find potential inflection points. So potential places where the function changes concavity and is continuous. Which from now on, we're going to be calling pips, potential inflection points. And as we saw last class, these things occur when f double prime equals to 0 or f double prime does not exist. Then we do the same thing as we did for the increasing decreasing test. We create a table of values. So we set up intervals using the pips, and we find the sign of f double prime on each interval. And then lastly, we apply the test. And so these are kind of the steps that we're going to follow every time we want to know about concavity. All right, so as soon as you guys have the guidelines written down as well as the example, let me know, and we will start with a pretty simple example right here. That was fast. It's 10 of you. Sandy Wandy. Wait, who's Sandy Wandy? Is that Sandra? I guess that must be Sandra. Okay, all right, so step one, we want to find and simplify the second derivative. So I'm starting with a really simple function right here so that we can focus on the process and less on the simplifying the derivative. The next examples we'll do will be a little bit more challenging in terms of finding the pips. So we're going to start off by f prime of x is equal to 3x squared minus 12. So then f double prime of x is equal to
6x.
6x, not 9. So we have 6x here. So then our second step, we want to find our pips. So we're setting f double prime equal to 0, which is like setting 6x equal to 0, which gives us x equals 0. And then we want to know where f double prime does not exist. Does that ever happen?
No.
Never. You got it. So the answer here is never. So we have one pip, and that pip is x equals to 0, which brings us to our third step. And it's going to look really familiar. We're going to have I for interval. And we use that 0 to separate the interval negative infinity to infinity. So I have negative infinity to 0, and then I have 0 to infinity. And so then that's my test value. And then I'm going to have, this is the main difference. Instead of having f prime there, I have f double prime.
If I'm correct, though, in the future, we'll end up putting this and the other part together, right?
I actually tend to keep them separate. You can.
Okay.
You can put them together, but I actually tend to keep them separate just because I find it less confusing and people like to make less mistakes.
Yeah, it's smarter that way.
Okay, so negative infinity to 0, what is a good test value here?
-1.
-1, and then, hello, Ellie. And then between 0 and infinity?
1.
1. So now the main difference between what we're doing here and the last one is f double prime instead of f prime. So we are going to plug those values into f double prime and find a sign. So f double prime of -1 is negative, and f double prime of +1 is positive. So here I'm going to write my signs, negative, positive. And negative, is it happy or sad? Sad. He's sad. And then over here, he's back to happy. Okay. Does concavity change at x equals 0? So that is no longer a pip. It is now an inflection point. So I can conclude, hey, look, concavity changed there. This is an inflection point. So to answer this question, we're going to say that it is concave up, which from now on we'll write as CU, on the 0 to infinity, and concave down, which we'll write as CD, on negative infinity to 0. And this is the first part of my answer. And the second part of my answer is that I have an inflection point at x equals 0. So inflection point, we're going to kind of write as IP from now on, IP, at x equals 0. But you'll notice that the word inflection point, the words inflection point, contain the word point, which means that we need a y value. So the same as when we were finding maxima and minima, we need a y value. Which function do I plug into to find y values?
The first?
You got it, the original function. So here I'm gonna have f of 0 is 0 cubed minus 12 times 0 plus 1, which is just 1. So my inflection point is 0, 1. And this, I'm sorry, I always forget to write step 4 here. Step 4 was when we actually made our conclusion about what the pluses and minuses told us. Okay, are there any questions about this problem? Hang on, 2 seconds, guys. Sorry. Okay, so next question. So this question was really straightforward. We didn't have much to do in terms of finding the second derivative, finding the pips. So in our next examples, it's going to be a little bit more challenging, and we're going to really focus on simplifying the second derivative. How do we find pips when it's challenging? So intervals of concavity and inflection points of f of x is equal to natural log of x squared minus 4x plus 40. And we know our step 1 is to take the derivative. Are there any log rules that I can use to simplify this?
No.
Yeah. Oh, wait, no. No.
No.
No, because there's minuses and pluses in the parentheses.
You got it, Alex. That minus and that plus inside those parentheses stop me from being able to simplify this thing. I can't bring the 2 down. I can't like separate this into additions. I can't distribute a ln inside of plus or minus. So I really just have to take the derivative as I see it. So f prime of x here is 2x minus 4 over x squared minus 4x plus 40. And then we take our second derivative by doing a chain rule. There's really not much I can do to simplify what I have there. So I do the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. Do I have a greatest common factor in the numerator? Because I know I have to simplify this, so. Do I?
Sorry, because you said it was a chain rule. Is it a quotient rule?
Did I say chain?
Yeah.
Definitely meant quotient. Sorry.
Okay.
Sorry. Definitely meant quotient. My bad. Sorry. Yes, we did a quotient rule there. Now, do I have a greatest common factor in my numerator?
Two x minus 4.
So I've got two 2x minus 4s on the right side, but do I have any on the left side of the minus sign?
We have no greatest common factor.
So technically I have a 2 as a greatest common factor, but if you don't see that, it's really like, it's not a big deal. In this case, factoring 2 out doesn't change anything. It's not like I have a whole factor that I can factor out, which means that in this case, I really just need to expand and combine like terms. So I'm going to end up with 2x squared minus 8x plus 80 minus 4x squared plus 16x minus 16 over x squared minus 4x plus 40 squared. And then I'm going to combine like terms to give me negative 2x squared plus 8x 80 minus 16 plus 64. And so this is a really great form for taking the third derivative, but it's not the best form for finding my pips, because I can factor that polynomial up top. And factored is better for solving equations than not factored. So we're going to keep going and we're going to factor this thing. So I have a 2 that I can factor out, -2, so I get x squared minus 8x, minus 4x minus 32. So how does this polynomial factor? I want two numbers that multiply to give -32 and add to give -4. What two numbers do that?
8 and 4.
Which one's going to be negative?
8.
Good job, guys. Good job, Cam and Ellie. So -2, x minus 8, x plus 4, over x squared minus 4x plus 40 squared. And that is my simplified second derivative. So factored is better for finding pips. So this brings us to our step 2, which is to find those pips. So that means we're setting f double prime equal to 0, which is like setting the numerator equal to 0. So here I have -2 times x minus 8 times x plus 4 is equal to 0. And what values do I get?
8 and minus 4.
You got it. So I get x equals 8, x equals -4. And then f double prime does not exist is like setting the denominator equal to 0. So here I'm like setting x squared minus 4x plus 40 is equal to 0. Maybe some of you asked yourselves the question when we were factoring the numerator before, why don't we factor the denominator? And if you didn't ask it, it's not a big deal. But the answer is that we didn't factor the denominator because we can't. This never equals 0. It does not factor. So how do I know that? How can I check that? Do you guys remember the quadratic formula off the top of your heads?
Yeah. It's going to be a root of a negative number.
You got it, David. What goes under the square root in the quadratic formula?
B squared minus 4ac, which would be
Got it.
all positive numbers minus like something that'll give it negative.
Exactly that. So like if that b squared minus 4ac is negative, which it is in this case, then the polynomial doesn't factor and it never equals to 0. So if b squared minus 4ac is less than 0, then the polynomial doesn't factor and never equals 0. So this is a good way to check when you're looking at a polynomial and trying to factor it. It's a good way to check if it has any solutions. So here I could be like -4 squared minus 4 times 1 times 40 is clearly negative. So the answer here is never.
For your f prime is equal to 0, you have x is equal to 4. It's minus 4.
Oh, my bad. I forgot to write the minus sign. I did. We know how much I love negatives. Okay. So here I ended up with 2 pips. They are -4 and 8, which means in my step 3, we're going to create our interval using those values. So I'm going to have -∞ to -4, -4 to 8, and 8 to infinity. And then I'm going to pick a test value on each interval. And then I'm going to pick f double prime. I'm going to find the sign of f double prime on those intervals. And I'm going to conclude things about f. What's a good test value on the first interval?
-5.
-5. What's a good test value on the second interval?
0.
0. If 0 is on your interval, you should just pick it. It's so easy to plug in 0, like so easy. It's also pretty easy to plug in 1, so that wouldn't be a bad value either. But like 0 is definitely the easiest value to plug in, so you might as well just pick it. So we're going to pick 0 there, and then we're going to pick 9 here. And so then I'm looking at f double prime of -5. Now notice, my second derivative is factored in the top, which makes it really easy without plugging this into my calculator to see if it's positive or negative. Because -2, well, that's negative. -5 minus 8 is clearly negative. -5 plus 4, also negative. So it's easy to look at each part and say if it's positive or negative. Is the denominator ever going to be negative?
No.
It's being squared, it's positive. So here I have 3 negatives and a positive. That gives me a negative value. Now f double prime of 0, I have -2, 0 minus 8, 0 plus 4, and then the denominator is always positive. So we're back to being positive. Well, we are positive here, rather. And then we can do the same thing for 9. We have our -2. 9 minus 8, well, now that's positive. 9 plus 4, and the denominator is always positive. So that's negative. And so that gives us a really quick way of looking at the thing and determining if it's positive or negative. And then we know that negative is sad and positive is happy. Does this thing have any inflection points?
Yeah.
2 of them.
2. Yeah.
Where are they? What x values?
-4 and 8.
-4 and 8. And so those are the values. Those were my pips. They're no longer pips. They are now actual inflection points. So I'm going to write IP down there. IP. And then that was our 4th step, that conclusion that we made. And now we'll write our final answer. This is concave up on -4, 8, and it is concave down on -infinity, -4, union 8, infinity. Oops. And then my inflection points are at x equals to -4. So if I plug in -4, I get ln of -4 squared minus 4 times -4 plus 40. Which is ln of 72. And at x equals to 8, which is also ln of 72. So my 2 inflection points have the same y value. Do you think that if you write a decimal instead of ln 72, you'll get full credit? No, you won't. You guys like decimals. You guys keep losing lots of points for decimals on your group work. Be careful, guys. No decimals. Ln of 72. I want exact answers here. So, any questions? All right, I'm going to write down the next question. Let me know when you are ready to do it. So we're going to do this one last question, and then we're going to go back and look at each of these problems and make another conclusion using the second derivative. Let me know in the chat when you are ready to do the problem. You guys are funny. Cold. Hilarious. I hope that's not true. All right, that's a lot of you done, but still not quite all of you yet. I think it's enough. Okay, we're gonna move on. So, step one, take the derivative and the second derivative and simplify. So here this is gonna be, we're gonna have to remember some stuff about how e works. So f prime of x is 12 e to the x minus 2 e to the 2x, and f double prime of x is 12 e to the x minus 4 e to the 2x. So far, so good? Now I want to simplify this thing, and I want to do that by factoring out the greatest common factor. But factoring out the greatest common factor, it's going to be easier to see if we remember that e to the power of ab is equal to e to the power of a to the power of b. Or it could be equal to e to the power of b to the power of a. So why is that important in this case? Because it's telling me that e to the 2x is the same thing as e to the x squared. Which means that this right here can be written as 12 e to the x minus 4 times e to the x squared, which might help us more easily to identify the greatest common factor, which is
4e to the x.
4e to the x, you got it. So we can see that there's an e to the x that's part of that factor. So then when I factor out the 4e to the x, what's left over?
Three minus e to the x.
You got it, 3 minus e to the x. And that is my simplified second derivative. Are there any questions about how I got that and the rule that I used with e to understand that? Good. Then we can move on to our second step, which is f double prime is equal to 0. So here I have 4 e to the x times 3 minus e to the x is equal to 0. Does e to the x equal 0 ever? No. We saw this actually in one of the problems that we did last class, and we had a big star by it. Remember that e to the x never equals 0. That's something that you should just be comfortable with. So that never happens. This, however, does happen. Now the question is, how? So back when we were doing logarithmic differentiation, we saw a rule actually that's going to help us to figure out how to solve this. Does anyone know how to solve this?
You do ln 3 is equal to x.
Exactly that. So good job, Xavier, good job, David. We saw before that ln of e to the a is just equal a. we saw that ln and e cancel each other out, which means that here I can actually do ln of both sides to isolate my x. So x is going to equal to ln 3. So in other words, to isolate x from e, we do ln of both sides. Hello. I don't know why it's been doing that. It's been doing that a lot lately. Just like starts over. Okay, so to isolate x from e to the x, we want to take ln of both sides and get x is equal to ln 3. And now we're going to set up our intervals. And that intervals, actually I forgot to write this part, my bad. Does f double prime ever not exist?
No.
No. So here we can just say never, and we only got one pip, x is equal to ln 3. Okay, so on my intervals here, my first interval will be negative infinity to ln 3, and my second interval will be ln 3 to infinity. And then I want to pick a test value on each of those intervals. Okay, to pick a test value on each of these intervals, it might be easier if we understand what value ln 3 represents. So ln 3 is approximately 1.098. So this would be a good time to go into your calculators and actually get a decimal. So then it helps me to pick what's a good value between negative infinity and ln 3.
0.
0. If 0 is on the interval, pick it. And what's a good value between ln 3 and infinity then?
2.
2. We could pick 2, we could pick 5, it really doesn't matter. Picking 2 is pretty straightforward. Good. And then we plug this in to f double prime. So I'm doing f double prime of 0. F double prime of 0 is equal to 4e to the 0, 3 minus e to the 0. And that gives me a positive value. And then f double prime of 2 is equal to 4e squared, 3 minus e squared, which gives me a negative value. So then we can make our conclusion about concavity.
So what's e to the 0?
E to the 0 is equal to 1.
Okay.
You don't really need that for this because probably you're just plugging it into your calculator to get a sign anyway. But yeah, in this case, e to the 0 is 1. E squared is some like bigger number. What is e squared? 7.3890560099. Okay, does this thing have any inflection points?
Yes.
Yes, that ln 3 is my inflection point. So first we can make our conclusions about concavity. So this is concave up on negative infinity ln 3, and it's concave down on ln 3 infinity. And this is my final answer here. Now remember, for the inflection point, I need to find a y value. And my inflection point is at x is equal to ln 3. So I plug that ln 3 into my original function. So I just briefly want to talk about how to solve this. What does e to the ln 3 equal? We just kind of talked a second ago about how e and ln cancel each other out. So if e and ln cancel each other out, what is e to the ln 3?
3.
It's just 3. You got it. Okay. So this is equal to 12 times 3. Now I'm going to go over here. We also have this rule that says that ln of a to the b is equal to b ln a, right? Right, this is one of our log rules, our 3 log rules that we used. So if I think of 2 ln 3 over here, how can I move backwards? It would be ln of what?
Three to the power of 2.
You got it, 3 to the power of 2. So that thing on the outside, so typically what we've been doing in this class is bringing powers out to the front. But I can actually also bring powers back inside. So I can think of this as minus e to the ln of 3 squared, which is what? If e and ln cancel each other out, then
3 squared.
9.
9, you got it. So this is 36 minus 3 squared, which is 9, and the answer is 27. Right? So you can plug that into your calculators, but it is good to have some intuition as to how the e's and lns work together. So my inflection point then is at ln 3, 27. And I am expecting you to give me a 27 and not just this. Okay, are there any questions about that? So lns and e's just cancel each other out. Like our rule that we have here is basically the same as what we had up here. We know that ln of e to the a is equal to a. Well, e to the ln a is also just equal to a. I can just cancel out the lns and the e's. We're going to, Ellie, just not in this. We're going to learn a new theorem. We're going to go back and look at each of these, and I don't know if I'm going to get to it today, but if not, the next class I have an example that has a square root in it planned. Okay, so the second derivative tells us concavity, but via this, it also gives us another way to check for local max and local min. So we're going to learn something now that's called the second derivative test. And we're going to go back and look at each of these problems and apply the second derivative test. So the second derivative test. So what we were just doing is not the second derivative test, it's the test for concavity. Let's say, to understand what the second derivative test is going to tell us, let's say that I have a function that looks something like this. How many critical values does this function have? Remember, critical values are where f prime is equal to 0 and f prime does not exist.
2.
It's got 2, you got it. One of them is right here, and one of them is right here. So there are 2 critical values. And what is the derivative at both of those critical values?
0.
F prime is equal to 0, f prime is equal to 0. At the first one, at my first critical value, is the function concave up or concave down?
Concave down.
Concave down, so it's sad. So what can I say about the second derivative there?
It's
Yes, Kim.
negative.
Negative.
Yes, it's negative. So here my second derivative is negative. What can I say about my second derivative at the second critical value?
Positive.
Where it's positive, exactly. So let's look at this. If my second derivative is negative, then that means it's concave down. If I have a critical value on that interval, is it possible that it's a min? That critical
Yeah.
value, is it a max or is it a min?
Minimum.
Are you sure? Look at it. Is it higher than the things around it or lower than the things around it?
It's higher, but it's a second derivative, no?
Right. But the critical value, where f prime equals 0, is a maximum. What about if f double prime is greater than 0? So in other words, what I have is concave up. On that interval, if I have a critical value, is it a min or a max? Did I just draw a min or a max there?
Min.
Are you guys with me? Like, so basically what we're saying is that's a max, that's a min. What I'm saying is there's this relationship between concavity and whether my critical values are maxes or mins. So this first critical value I had right here, before I even thought about the second derivative, I was like, hey, look, that's a critical value. It's a max. It's a max because it's concave down. And so this is what the second derivative test tells us. It gives us this relationship between concavity and critical values. So in other words, there's a relationship between concavity and whether a critical value is a max or a min. And that is what the second derivative test tells me. So we're going to actually state the second derivative test. It tells me that if f prime of x, or f prime of c, we'll say, my bad, if f prime of c is equal to 0, so in other words, I have a critical value that represents a horizontal tangent line, and f double prime of x is greater than 0, then I have a concave up situation, and clearly I have a minimum. F double prime of c, my bad. Then x equals c is a local min of f of x. If f prime of c equals 0 and f double prime of c is less than 0, so in this first one I had this concave up situation happening, so I had my min there. In this case, I have a concave down situation happening. Can I restate the green? Yeah, give me just a second, Xavier. Then x equals c is a local max of f of x. And c if f double prime is equal to 0, then the second derivative test is inconclusive. And lastly, I'm just going to put this out here to make sure that you guys follow. We're really only looking at critical values where f prime equals to 0. This does not apply to critical values where f prime does not exist. So wait, do you want me to restate it or re-explain it, Xavier? Is it just that you can't read it? Okay, it says there is a relation between concavity and whether a critical value is a max or a min. And I'm going to give you guys a second to copy this down. I have to go, I'll be right back. Hello, Sandy Wandy. All right, you'll have this down? Good. Okay, so what we're going to do now is we're going to go back and look at all of the previous functions that we just did and apply the second derivative test. There were just 3 of them, so we'll say apply the second derivative test to the previous 3 functions. Okay, so our first function was f of x is equal to x cubed minus 12x plus 1. F prime of x is equal to 3x squared minus 12. And f double prime of x was equal to 6x. So I'm just going to rewrite all this stuff down here because there's not going to be space if we go back to each one. So what the second derivative test is telling me to do is to go back to the first derivative and find the critical values where f prime equals to 0. So here I'm really just looking at f prime equals to 0. So I'm taking 3x squared minus 12 and setting it equal to 0, which gives me x squared is equal to 4, which gives me x is equal to plus or minus 2. So if I'm thinking about critical values, f prime does not exist is not important for the second derivative test. And so this is kind of our first step that we have right here, which is set f prime equal to 0. And then we're going to take those values and plug them into the second derivative. So I'm going to be looking at f double prime of 2 and f double prime of negative 2. So f double prime of 2 is positive. I don't care about the value, I just care that it's positive. And f double prime of negative 2 is negative. And if it's positive, that means it's concave up. And if it's negative, that means it's concave down. So 2, is that going to be a max or a min?
Minimum.
It's going to be a minimum. And negative 2?
It's gonna be a maximum.
Is going to be a max. And drawing that concavity actually can help me to see that. I just like draw a little concave up and I'm like, oh, hey, look, this is clearly a min. So we're able to make our conclusion then that this has a min at x equals 2. F of 2 is 2 cubed minus 12 times 2 plus 1, which is 8 minus 24 plus 1. So my min is at 215, and then I have a max at x equals to negative 2. This gives me negative 8 plus 24 plus 1. For 17. And we got those max and min without having to do the table of values with the first derivative. We just had to plug in to the second derivative. And so this just gave me another way of figuring out whether my critical values are max or min. Is it making sense? Are there any questions about this? Okay, so I'm just going to go up really quickly back to where we originally started with this function. And this is what we did here. If I were to try to draw a graph of this thing just from what I have no clue what this looks like, but I know that it's concave down and then it's concave up. So all the second derivative test is telling me is that what we could have seen just by graphing, that that's got to be a max and that that's got to be a min. Okay, any questions about that? So we're going to do the second derivative test on all of them just to kind of get used to it. And then if we have time, we'll do a new problem where we like start from scratch. Here I have f of x was equal to ln of x squared minus 4x plus 40. Then f prime of x was equal to 2x minus 4 over x squared minus 4x plus 40. And then f double prime of x was negative 2 times x minus 8 times x plus 4. So our first step, then we said, is to find our critical values where f prime is equal to 0. So I have f prime equals 0, which means I'm going back to f prime here. So I'm really only looking at where 2x minus 4 is equal to 0 to give me an x equals 2. Do I care about where f prime doesn't exist?
No.
I do not. Good job. So then I move on. I want to plug this value, f double prime of 2, into the second derivative. So here I have negative, 2 minus 8, that's negative, 2 plus 4, that's positive, and this is positive, so this is greater than 0, so it's concave up. So is x equals 2 a max or a min?
Minimum.
A minimum, you got it. So that's a min, so we can say that there is a local min at x equals 2, and f of 2 is ln of 4 minus 8 plus 40. So 2 ln 36 is my local min.
How would we be able to know if it's global or local?
So we actually don't know from this if it's global or
Okay.
local,
Yeah.
but we've said that a global min or a global max are also considered local as long as they're like not in points that we saw for the extreme value theorem, right? Because we said the local, the definition is that it's just higher than everywhere else around it. And so that's also going to be true of a global. So like in terms of this, I don't know immediately. Okay, I'm just going to go back and look at the function here where we did this here. So here we had that it was concave down and then concave up and concave down. And the only place where there was a minimum or a maximum was between negative 4 and 8. So I can assume that this probably looks something like this. All right, where we have a min there, but then on these intervals, there are no critical values. So there is no place where I'm going to have a min or a max. Okay, I want to look at the next one here. So here we're trying to find out if the critical values represent maxes or mins. If my critical value occurs between negative infinity and ln 3, is that going to be a min or a max?
Min.
Going to be a min. Good job, Alex, because when I look at that interval, I see that it's concave up on that interval. So if there's a critical value on that interval, it means that that's going to be a min. Where if I have a critical value that occurs on the other interval, that critical value will be a max. So we're going to go and we're going to find those critical values and just see which intervals they occur on. We're going to redo the process for C here. So here I'm going to have f of x is equal to 12 e to the x minus e to the 2x. F prime of x is equal to 12 e to the x minus 2 e to the 2x. And f double prime of x is equal to 12 e to the, I'm sorry, we'd already simplified that one. So this is 4 e to the x times 3 minus e to the x. And so now for step 1, I'm once again looking at f prime to find my critical values. So here I'm saying f prime is equal to 0. And I'm going to need to simplify this f prime. What is the greatest common factor here? Based on what we did to find the greatest common factor for f double prime.
2ex.
2e to the x, you got it. And that's because this is the same as 2 times e to the x squared. So here I'll have 2e to the x times 6 minus e to the x is equal to 0. So here I'll end up with e to the x equals 0. Does that ever happen?
No.
No. So this is never. And then over here I have 6 minus e to the x equals 0, which gives me e to the x equals 6, which based on how we solved before, what's that going to give me?
Ln 6.
Good job, guys. Ln 6. So I'm taking ln of both sides, so I get that x is equal to ln 6. So then I'm trying to figure out which one of those intervals it's on by plugging it in to the second derivative. So I'm looking at f double prime of ln 6. And so I have 4e to the ln 6 times 3 minus e to the ln 6. And that is less than 0. So is that a min or a max?
Max.
Max. So here I have a max at x is equal to ln 6 that we need to plug in now. So I'm going to have f of ln 6 is 12e to the ln 6 minus e to the 2 ln 6, which is 12 times 6 minus e to the ln of 6 squared, which is 72 minus 36. So my max is ln 6, 36. Okay, are there any questions about this? Okay, so then we're going to do one last problem. In next class, we'll do, Elliot asked for one with the square root. I don't want to rush through a square root one because there's a lot of things that we're going to have to think about with that one. So we're just going to do one problem where we do the second derivative test without anything else from the beginning. And then next class, we'll do a few more problems. And then we're going to start combining all of this stuff together to sketch some curves. So clearly we need our derivative. So I have f of x is x squared times x minus 4 cubed. What rule do I need to use to find my derivative here?
Product rule.
Product rule. So I'm like f prime of x, the derivative of the first times the second, plus the first times the derivative of the second. And since I'm about to take another derivative and I want to find where f prime equals 0, do I need to simplify this?
Yep.
What's my GCF?
X minus 4 squared and x times x minus 4 squared.
You got it. So there's an x on both sides and there's x minus 4s on both sides. We take the lower power. So I get that this is x times x minus 4 squared times 2 times x minus 4 plus x times 3. So this f prime of x is equal to x times x minus 4 squared times 5x minus 8. Is this the best derivative for taking a second derivative?
No.
Is this the best simplification for finding where it equals to 0?
Yes.
Yes. So the best simplification for finding where it equals to 0, factored is better. However, for finding another derivative, less product rule is better. So this is factored form to find f prime equals 0. But then I'm going to take that x and distribute it through into that part. And this is going to be better for finding a second derivative, because I got rid of like an extra product rule that I had. So now I'll do f double prime of x, and I get 2 times x minus 4 times 5x squared minus 8x plus x minus 4 squared times 10x minus 8. And I do not need to simplify my second derivative because I'm not setting it equal to 0 ever. And I'm not finding another derivative. I can leave it like that and that's fine. Okay, so this brings us to our first step, which is to find where f prime equals to 0. So now I'm saying f prime equals 0. So that's x times x minus 4 squared times 5x minus 8 is equal to 0. And what values do I get here?
0, 4, and 8 over 5, I think.
Yes, does everyone see that? Do I need to like actually do out the 8 over 5 one? Okay, so then in that case, now I'm taking these values and plugging them in to my second derivative. Do I care about where f prime doesn't exist?
No.
No. So remember we said the second derivative test doesn't apply then, nothing to think about. So now I'm saying f double prime of 0, and then I want f double prime of 4, and f double prime of 8 over 5. So I'm plugging those in to f double prime now. And am I looking for a value or a sign?
Sign.
A sign. So here you can plug this into your calculator. Simplifying might actually make it easier to find a sign. So if you want to simplify, you can, but you don't have to. So I'm going to go down here and say just however, it might make it easier to find the sign. So I'm just going to give you the signs. In this case, f double prime of 0 is less than 0, so it's concave down. This is equal to 0, and this is greater than 0, so it's concave up. So is 0, what if, we're going to answer that in just a second, Kiana. In the first one, is 0 a max or a min?
Max.
That's a max because we have our little value up there, that's a max. And is 8/5 a max or a min?
Minimum.
That's a min because it was concave up. I'm just going to go back and bring the second derivative test up for us to look at. It said that if the answer is 0 when we plug in, then the second derivative test is inconclusive. So in this case, we don't have anything to say about 4, just that it is inconclusive. So here we have a max at x equals 0, which we want to plug in. So I plug in 0 and I get 0 squared times 0 minus 4 cubed, which is just 0. So my max is 0, 0. And then I have a min at x equals 8/5. So I'm looking at 8/5. 8/5 squared times 8/5 minus 4 cubed, which I did for us because it's gross, negative 110,592 over 3,125. So my min is there. And this is my final answer. Are there any questions about this? Okay, so today we learned 2 main uses of the second derivative. The second derivative tells us concavity, so we can use it to find the intervals of concavity, but we can also use it to figure out if critical values are maxes or mins. And next class we'll do a few more examples of this, and we will deal with the square roots and do some things that are not fun to simplify. And then we'll start sketching curves. That is all for today.